Welcome to Drinking Bros, presented by GhostBed.com.
Welcome to a very special edition of, I don't know what show this is, actually. We'll put it up everywhere, actually, because this is Dr. Brian Keating. We're going to do a little catch-up on all things science. Obviously, the James Webb Space Telescope is up there taking awesome pictures, and you've actually got a giveaway that you want to do. So you produce quite a bit of science content, trying to be a communicator. There's a lot of guys in the science community who are enthralled by the work itself, but also in communicating, like yourself, Brian Greene, Brian Cox, Hakeem, Neil, all these guys that you can tell that you guys love science so much that you just want to tell everybody about it, which I think is great. Like, that's the best proselytizer, I guess, is always the person that's really infatuated with the subject matter. And in this case, science literacy is so important, right? So you got a giveaway. Explain your giveaway for everybody.
Yeah, I want to come in hot with you, Dan. First of all, it's really good to see you, and just loving everything you're putting out on Twitter, keeping us sane out there,
Yes,
being a voice of reason and also of science, and really appreciate you, man.
Yes, sir.
But yeah, I want to come in hot, so I got a giveaway just for citizen listeners, and that is literally came in hot. It was formed about 4 billion years ago. It's hard to get my vlogging camera to focus in on this. I got this from Zuby. Zuby gave me this recommendation for this camera, and it doesn't really focus super well. But anyway,
I like how you're
this
blaming him for it. That's awesome.
So this is a meteorite that fell to Earth, if we think about 5,000 years ago, and as part of a fragment of a multi-ton meteoroid that crashed into Argentina. Now, this was formed about 4.5 billion years ago in the solar system, in the proto galaxy that was our Milky Way. And it condensed and formed and just luckily wasn't big enough to further exterminate the humans that were living back then, like the Chicxulub impact did 65 million years ago to those poor little dinosaurs. So what I want to do is, for your listeners who join my mailing list at briankeating.com/list, is I'll send out an actual meteorite sample like this, space dust, if you will, to the first 100 people that join the list. And I can only do it to U.S. addresses only. I'm just a humble, public servant, as you know, working at the state of California for Governor Gavin Newsom. But it also can go to APO office. So I want to especially send this out to my military brothers and sisters, who I am really just so appreciative of and love the work that you do. And actually, you hinted at this. So a lot of these people that do the work that you mentioned, first of all, you mentioned 2 other Brians. Do you know how it feels to have 2 other Brians be your kid's favorite Brian astrophysicist? I mean, it freaking hurts, man. Yeah. But besides that, those guys are all wonderful geniuses, but they're theoreticians. So what distinguishes me and what my group does and my team does, we have over 20 people just here in UC San Diego, and we have 300 that are working in Chile to build the world's best cosmic observatory called the Simons Observatory. That distinguishes us by the fact that we build telescopes. So these theorists can come up with crazy ideas, and they can basically do it at zero cost to themselves.
Right.
And so what I want to do at zero cost is give back to the people that are paying my salary. Yes, I'm a humble public servant, but any scientist worth their salt has to give back, because otherwise you're kind of like a moral coward, in my opinion, that you're just taking money. Every scientist, I don't care who. I mean, I'm sponsored by a private foundation primarily, but all of us got our training thanks to living in the world's greatest country, or even overseas. It's certainly true overseas as well. So anyway, I believe I have a moral obligation to share science at zero cost to the public, because you guys pay my salary, and I would do what I do for free. And I think that's what you were harping on and continuing on. It's beautiful. You noticed that I would do this for free, Dan. So the fact that I get paid for it by you guys makes me want to contribute more. So join the list, briankeating.com/list. First 100 people, especially military folks, would love that. I can ship to APOs as well.
Sweet. Yeah, I agree with you. You got to keep the lights on, but I'm not a big fan of profiteering in commodities, and I think that science literacy is definitely a commodity. Now let's get into it. So the James Webb Space Telescope took 30 years to build, several dollars, but we're now seeing. Can you explain in general terms the biggest difference between Hubble and James Webb?
Yeah, so Hubble was launched. Well, first of all, Hubble was designed in the 1950s and 60s. It was conceived at that time. This telescope was obviously conceived after Hubble, and it has a very different mission. So the Hubble telescope had a mission to really observe the universe in the optical, the same exact wavelengths that our eyes can see, with additional capability that our eyes can't do, which is to see spectral decomposition, to see the actual chemical fingerprint of the objects it's looking at through what's called spectroscopy. The Webb telescope is seeing purely invisible objects. And these are things that you can't see because it's in the infrared. It's different than night vision goggles. So now NVGs work by amplifying ambient visible light. But your thermal imaging, they work at longer wavelengths that were unobserved until about 150 years ago. So we didn't even know it existed until the late 1700s, early 1800s. So there's a wavelength of light, slightly longer in size than visible light, and our eyes are invisible to it, but we perceive it as heat. So you can go outside when it's sunny. I'm sure it is in Texas right now. You can go out there, put your hand up, and know where the sun is without your eyes being open at all, right?
Sure.
So your hands have infrared sensors in them. They're called skin cells, and they have thermal sensation as well. Well, the Webb telescope has cameras that can only see infrared, and it can go out to 20 times the wavelength of what Hubble could see. And what that's useful for is twofold. On previous episodes, and when I did some explainer episodes last summer, which we got to do again, where you took questions from the audience and I answered them in front of my cheesy green screen here at UC San Diego. So some of the questions about redshift, and redshift means the expansion of the universe is continuing, so that a galaxy today is farther away from the Milky Way than it was yesterday, and will be farther so tomorrow.
But it's expanding like a balloon, right? Where I think this confuses a lot of people, and it is somewhat difficult to visualize, but it's expanding not from a central point outward, but everything is all expanding at the same time, which means not only are we're not the center and things are getting farther away from us, everything that exists is getting farther away from everything else.
That's exactly right. So there is no center to the universe. There is a center to the solar system, if you like, but there's no center to the universe. And that's kind of difficult concept to grasp. And so you made this analogy, the surface of a balloon. So do imagine that you have a balloon and you put little dots in the shape of spiral galaxies on it, and then you inflate the balloon. Each galaxy moves away from each other galaxy. So the natural thing, if you're an egomaniac like me, is to think that, I see everybody's moving away from me. I must be the center of attention. But if you think about it, every single spot on that balloon can make the same claim. And when that's true, mathematically and logically speaking, there is no center. Now, the analogy breaks down because the universe that we traverse in is three-dimensional in space, and then we have an extra fourth dimension of time. And so the skin of the balloon is only two-dimensional. So you have to kind of decrease your dimensionality by this projection onto a flat surface, a two-dimensional surface. Even though it's curved, it's flat in terms of its local behavior. So yes, it is true that every point in the universe is moving away from every other point. And by the way, we haven't known that for more than 90 years. So it's not like humanity has always known this. So Hubble himself, the man, Edwin Hubble, discovered that every galaxy in the universe, with a literal handful of exceptions, so there's literally hundreds of billions of galaxies, every single one of them is moving away from us except for about 10. So the good approximation is that we are not the center of the universe, because in each galaxy, they could make the same claim.
Right.
Now, not only are the galaxies moving down, but as you know, anything in space is also getting expanded, including light waves. So if you have a wave, you think about a wave on the ocean, imagine the ocean just suddenly got stretched. So some wave that had a set period of a minute or so, now it might be 2 minutes. So that takes something that initially was like a star in another galaxy producing light, just like our sun, yellowish, greenish light. That would be stretched and become slightly redder. That's where we get the name redshift from. So it's a consequence of the expansion of the universe, ushered in by Hubble himself, after whom the Hubble Space Telescope was named. So the Hubble telescope did a lot, and is still doing a lot, but it had many, many limitations, one of which was that it could only see visible light, mainly visible light. And there's a lot more in the universe that is deeper, farther away, and has expanded more that Webb can see.
That's really incredible, because the difference between Hubble, which is primarily an optical telescope, and James Webb has multiple capabilities, right? So it's going to be able to capture multiple, light wavelengths. The ability to block out everything but infrared allows you to isolate and see farther, right?
Yeah, that's right. It can see farther back, and it can see things that is essentially invisible, but it can also see things that are just as close by as Jupiter or objects in our solar system. So just this past week,
Yeah.
I had a conversation with the lead project scientist who won the Nobel Prize in 2006 for a different project. I had him on the show, and we were talking about the upcoming results on imaging objects in our solar system. Now, why would you take I mean, imagine this, Dan. The telescope's 20 feet in diameter. It's bigger than the room that you and I are sitting in, right? It launched into space on a rocket that was only 15 feet in diameter. How the heck does that happen? So on my YouTube channel, Dr. Brian Keating, I've done a lot of animations about how this actually worked, how the launch process worked. But in reality, the telescope had to do things that Hubble could hardly dream about, and that's because of where it's located. It's located at a very special point that's mind-bendingly kind of exotic, that even genius scientists much smarter than me were able to conceive of such a location. So check this out. Most things that you know about, including the moon and the earth, they're orbiting around something else, a physical object, a chunk of rock in the case of the moon orbiting around the earth, or a ball of glowing hot nuclear fusing material like the sun. But the Webb telescope is orbiting literally around nothingness. So the Webb telescope is 1 million miles from Earth. So today we're talking July 20th, which is the 53rd anniversary of men landing on the moon back in 1969. So I got to give them a shout out. And that the moon is 4 times closer than the Webb telescope. Now, human beings have only been out to the moon. That's as far as human beings ever went. So imagine we couldn't go 4 times out to service this telescope. And you're a lot younger than I am, but I remember in 1990 when the Hubble telescope was launched, it had blurry vision, basically. It had astigmatism. So that thing had to be fixed. Now, why could it be fixed? Because it was kind of like this boondoggle that NASA wanted a project for the shuttle, which is going to low Earth orbit, 250 miles above the Earth's surface. That's closer, much closer to Earth than you and I are right now. We're 1,000 miles away. So we're 4 times farther away than the Hubble telescope is when it goes overhead. Now, it was put there because it was thought that it would need to be serviced. And indeed, it did need to be serviced soon after it was launched. The Webb telescope, forget about it. Not only can it not be serviced by astronauts because no one can get out that far, and no one will be able to do that probably ever, because of the way it's orbiting around this empty spot of space, like a parking lot called the Earth-Moon Lagrange point number 2. But it had to assemble itself like a piece of freaking origami. It's a robot telescope that is self-assembled, aligned to smaller than a human hair precision, and is taking images that Hubble couldn't take. So yes, this is the most expensive thing ever launched into space. It wasn't just $1 billion. It was $10 billion just to build. And as you know, you go to an aircraft carrier or something like that, you don't just build the aircraft carrier to have it. There's a rule of thumb in big project construction projects. It basically takes 10% of the project construction cost to operate the damn thing. It could be it's a rule of thumb that works on power law basis. So it works on many different situations. My observatory, the Webb. So this thing costs about $1 billion a year, which means that it will double its cost every 10 years. So this is a very expensive. It's more expensive than the Large Hadron Collider where the Higgs boson was discovered, and it's in space and it assembled itself. So good on NASA for doing this.
Well, speaking of the LHC, so with CERN, we knew what we were looking for. I think quarks, subatomic particles like Higgs boson and shit like that. Theoretical physicists, like you were talking about before, theoretical physicists came up with the concepts, and then LHC was built to test these because an unfalsifiable claim in science is nothing at all, right? So this is what you do, except with telescopes. So you're uniquely positioned here to answer these types of questions. What are the discoveries that we should expect to see, or what questions are we looking to have answered by James Webb?
Yeah, it's really perceptive that you mentioned that, because for the most part, a scientist shouldn't say what he or she wants to discover. I was on a different podcast, to be named some other time, Neil deGrasse Tyson. And they were asking me, what do you hope to see with the Simons Observatory, the project I co-lead with these 300 people around the world, looking for different signals than the Webb telescope. And I said, that's a very dangerous question. It's like, if you say, like, what do you want to see, when you come home early and your wife or your girlfriend's upset, like, you want to see nothing. Like, you don't come into it. If you do come into it with an expectation, you're going to get a very different, you can open yourself up to what's called confirmation bias.
Sure,
now, we academics make up a lot of BS stuff with I have to get 2 hours of mandatory anti-bias training, sexual harassment training. At the University of California, we have training for everything. And I'm like, I already know how to sexually harass people. I don't need, no, I don't. I'm just kidding. Gavin, please, brother, don't shut me down. But the point being, there are biases that are real. And one of them is a scientifically predilection for us to see what we want to see. And in fact, my first book, Losing the Nobel Prize, was all about that, how I wanted to win a Nobel Prize so badly that, we built this telescope at the South Pole, Antarctica, where I've been twice. And that telescope is designed to see something specific. So I'd be lying if I said I didn't want to see what I built this thing explicitly to see. Now with Webb, I happen to have a different interest, which dovetails into the meteorite giveaway, briankeating.com/list for your listeners. And that is I want to search for the signature, the imprimatur of life itself. Because what we're doing is closer to the beginning of time when we study the cosmic microwave background. Because the wavelength stretching effect that's called redshift that you and I have discussed many times, that means even longer wavelength than light is infrared, and even longer than infrared is called microwaves. And it's just like the microwaves in your oven in your kitchen. The infrared can see things that are very far back, but the microwave background that I study, building telescopes in Chile, Antarctica, and in space, can see back potentially to the very beginning of time. So I'm actually not looking to them for those kind of answers. Like, if you go to somebody, you're always learning from people, and I admire that. I think scientists should do that too. But in particular, I want to learn something that I don't know, and I don't have enough time to investigate, and that's called exobiology. That's the search for life on other planets, called exoplanets.
And is I assume there's a contingent of SETI that's involved in at least the data processing part, if not some of the actual projects that James Webb is going to conduct, right?
Well, so SETI is slightly different than what Webb is conducting. Certainly, if Webb tunes into a planet and they've got the Citizen podcast going on over there, it will see it if it's in the infrared and happens to be redshifted by just the right amount. Okay, so that would be obvious, right? Or if you image an exoplanet and you can see its surface and you see, there's some cities there, there's some object. Okay, so that's an obvious search for extraterrestrial intelligence. That's what SETI, SETI stands for. But typically, SETI is a more passive, observational, blind serendipitous search, where you're essentially looking anywhere, not targeting specific targets. So Webb is targeting specific, in some cases, known targets. For example, the image that they released last week, I'm going to try to screen share here. Let me see if this will work. So this is from my YouTube channel. Let's see if this works, please. Yeah, there we go. I don't know. Can you see that, Dan?
Yes, I can.
So I'm showing, if you're watching this, I'm showing a spectrum of an exoplanet, which has a pretty cool damn name. It's called the Wasp 96b planet. So it's a known exoplanet. It's about the size of Jupiter, and or half the size of Jupiter, except it orbits so close to its host star that it only takes 3 days for its year to go around this object's host star. So there it is. What they looked at is not to make an image to see if there's, cities there. I mean, it's very unlikely a gas giant like Jupiter would have, life and cities on it, but, who knows? But they looked at its atmosphere. They looked at how is its atmosphere responding chemically? What sorts of processes is it exhibiting that could potentially be harbingers of life, or perhaps it could be actual, byproducts of life. And a lot of scientists, myself included, do think that liquid water in some form is a prerequisite. It's not sufficient, but it's a necessary condition. So what they did is they took a spectrum. I'll pause it here. And you see in the spectrum, they have these different features. You see the wavelength of light on the bottom, where the wavelength is given in millionths of a meter, called microns. The human eye cuts out at about 0.7 microns, so it's far to the left there, and that shows you the power of Webb. Go beyond the visible spectrum that Hubble or your eye can see. Goes way out to the infrared, which is where these molecules will exhibit their classic behavior, indicating what chemicals are present. So in this case, there's water, and there's unambiguous detection of water, and it must be in atmospheric vapor form. It can't be in ice form or something like that. So now water is actually a greenhouse gas. It's actually much more potent in some ways than other greenhouse gases. So some people have suggested, let's use Webb and let's look for byproducts greenhouse gases basically on other planets, not water, because water is actually very common in the universe, but other things like methane and higher order hydrocarbons that would be not the byproduct of, an advanced civilization signaling to us, but maybe they discovered agriculture, maybe they have these prebiotic bacteria like we had. So this is the most interesting. Now, it's ironic because it's not the science I do. I study the cosmos, the origin of the universe. But I think we're in my field better positioned to understand the earliest moments of the cosmos. But there's fascinating science that Webb can do that we can never do by virtue of its design. That fascinates me even more in some ways than my own search is sometimes.
Yeah, I mean, that's the idea that there might be biological life elsewhere is... It's easy to be distracted by, right? I mean, it's now Wasp 96 is a gas giant, right?
Yeah, that's right. Just like Jupiter.
Yeah. So we wouldn't expect there to be life as we know it on there, but biological life, I mean, we know of extremophiles that can exist in like hot springs and things like that, or even close to volcanic areas. So
yeah, that's right.
The idea of, and we've seen plenty of life in the clouds in our own atmosphere as well. So the idea that there might be some what we would call an extremophile might be actually ordinary life in the atmosphere of a gas giant like that has water and other things like that, right?
Yeah, 100%. And actually, most of these planets, like Jupiter, has about 70 moons that surround it. Those are rocky orb-like planets that are actually heated by Jupiter's thermal emission. They have active tectonic plates on them. They have volcanoes on them. So some of these moons are actually thought to be, especially in the case of Saturn, which is another gas giant, has some moons that particularly have already been searched for life, Titan. And some people think there's a liquid methane ocean on Enceladus. So even though the planet itself may or may not support life in its gaseous atmosphere, you're right, it may have moons, although this one is so close to the host star, we're not quite sure it would be gravitationally supporting a moon. But nevertheless, the other ones, and this is just the easiest one to find. And why do they do this, by the way? Why do they look at a planet, that's guaranteed not to have? Well, we have to do as scientists to guard against confirmation bias. There's only one way to really safeguard as a scientist. And the famous scientist, Nobel laureate Richard Feynman said, the first principle in science is not to fool yourself. The second principle is you're the easiest person to fool. So we're always trying not to be Feynman's fool. And one of the ways that we do that is called calibration. So how do you know that what you're looking at is actually honest to goodness, the signal that you're seeing, and not some imposter? Well, it's probably what you used to do when you were like sniping and, and doing all that stuff and the fun, stuff that we talked about last time. But you have to sight in, right? So you have to calibrate. Well, there's so much wind drift, there's rotational effect, there's pressure gradient, stuff like that. So you do like a test shot, right? Now, I'm sure you would do this in the past. And then you sight it in, you hone it in, and then you know what's called your systematic error. How much are the effects, not due to things you're interested in, not due to like the enemy in motion or some other effect.
Just environmentals,
Environmental, 100%.
Yeah.
So what's the environmental effect of a space telescope? Well, there's still lots of sources of heat, of stray light, of variation in the sensors.
Gravitational lensing, stuff that you can't control no matter what you do with the telescope, right?
Exactly. Yeah. And actually, gravitational lensing, maybe we'll talk about that. That was one of the tools. So Einstein realized that the force of gravity is akin to the distortion of space and time. In other words, that massive bodies, they do affect the positions as seen from Earth of distant objects as light from behind them passes through and becomes visible to our telescope. So I'll show now. Let me see if I can get that going here. I'll show now what's called a very strong gravitational lensing, where you see these arcs, you see these whirls. And by the way, anytime you see something with these 8-pointed figures, those are alien civilizations. Those are I'm just kidding. Those are stars.
Those are stars in our own galaxy, right? That's why they appear so bright.
Yeah. Those are called point sources. So a star, basically, as huge as it is, it's so far away that they effectively look like single pixels. And so you get what's called diffraction spikes around them from the fact that Webb's telescope mirrors are shaped like hexagons, and then they're supported by these 3 beams that go out. So anything that doesn't have those spikes, Dan, means it's a galaxy or something much farther away to be a point source. So you see here these arcs and these weird-looking objects here. They're arcing around almost like in a circle, surrounding some other objects that aren't bent like that. So the ones that aren't bent are in the foreground. They are acting like a lens, bending the trajectory of light from farther away objects, those curved objects in the back. Those are traversing space-time, getting bent, deflected, like windage or whatever, and that deflects them enough to distort the appearance that we see. And for that reason, we call this gravitational lensing, and it's a consequence of Einstein's theory of general relativity.
I mean, it may be the aside from thinking about how time is warped by gravity, that might be the thing that really led Einstein to the miracle year in general, right? I mean, the just because he thought about it before he could see it, right? And it took him about 15 years to actually get the data because of World War I. A lot of weird shit was going on. It's a very interesting situation. I wonder, scientists these days, there's a lot more competition than there used to be, right? There's a lot more scientists. There's a lot more motives, I guess, for lack of a better phrase.
Pressure.
Yeah, there's a lot of pressure to publish as well. But
funding.
It always seemed to me, some of the greatest scientific breakthroughs come from trying to understand why what we know is true, right? So not just like, hey, I'm going to go do something completely new and figure out something completely new, but it's usually one person who becomes fixated on this is true, but I can't understand why it's true, and I need to know. That seems to be where a lot of the great discoveries really come from.
Yeah, in a lot of ways that's true, because if that's the pure kind of aversion to the confirmation bias. If you look for flaws in what's currently understood, then that's often, I tell my students, that's often a really good microscope into where you should direct your career. And I'll give the kind of following example. Aristotle, of course, all about, but he was actually wrong about almost everything in science. He thought that heavy things fell faster than light things. He felt that there were only 4 elements: earth, air, wind, and fire. So he had all these crazy ideas. But he actually had one idea that's still maintained. The only one I found in my research, and maybe folks out there can correct me, there's only one thing he got right in all of science, and that was that whales are mammals. Which is kind of cool. Now, how did he do that? He observed these objects called whales, right? And he saw their behavior, and he saw that they were, mating and milking, whatever I'm not a biologist. I don't freaking know. But the point being, he did observation. Now, why didn't the same genius? I mean, he was a real genius. I mean, he established the laws of logic, philosophy, even theatrical, the 3-act structure of plays, that came from Aristotle. Anyway.
We call it the A, B, and C plot now. That's the common language for that now. But yeah,
is it?
Yeah, he invented that before plays were really even a thing, to be honest. Before,
yeah, 100%.
What we know about modern plays mostly comes from like the 15th through the 17th century in England. So, anyways, continue.
Yeah, so they stood on. So I'm not hating. I don't want to cancel Aristotle. Don't get me wrong, man. But the point being, he didn't make observations in certain. So he had blind spots. Like we all have blind spots, and the biggest one is when you think you don't have blind spots, right? So Galileo came along and said, no, if I take a heavy object like 2 bricks and I tie them together, do they fall faster than 1 brick by itself? It's idiotic. So he did the apocryphally probably dropped on the Leaning Tower of Pisa, but anyway, he did observations. Now then Newton came along 80 years later and said, well, actually what Galileo thought about the tides on the Earth's surface is totally wrong. And Newton came up with the law of universal gravitation. Then, as you say, miracle year, Einstein comes along. He comes up with a correction to Newton. Newton was wrong. He thought gravity traveled infinitely fast. He thought things were pulling on each other. He didn't understand why the universe was static and how that was compatible with sort of his notions of theology at the time. And then we're coming along now and trying to overthrow Einstein, right? So that's the progress of science. Science is not the belief in the infallibility of experts. It's in the knowledge that experts are probably wrong, but that doesn't mean they're dumb or stupid or something like that. And as you say, if you can pick out what's thought to be true, but ain't necessarily so, then you have it made as a scientist, because you'll have an infinite supply of things to correct for all eternity.
For sure. So that leads me to a question that I've wanted to ask you. I've actually got a couple of questions I've wanted to ask you for a while, but one of them is, so there's something weird to me about the apparent flatness of the universe. What we know about gravity and how it shapes things. We usually see things in spheres, whether it be the dip in space-time or planets themselves or whatever. I've heard some theoretical physicists suggest that that might, because the universe looks flat to us, that might suggest that the universe is far larger than we think it is. So like think about for the audience.
Yeah.
Consider yourself standing on the Earth. It appears like it's flat, but it's only, we know that it's a curved surface. It only appears flat because of how large it is relative to our ability to observe it. So what are your thoughts on, because I've heard some estimation based on where we might anticipate the curvature of the universe to happen, that there's, instead of 200 or so billion galaxies, there might be more like 2 trillion galaxies. You know what I mean?
Yeah. So those are separate facts. So let's go to the first one that you mentioned. It's certainly true that it was not expected that the universe was so-called flat. And what does flatness mean? When you're on Earth, if you're in Austin, I'm in San Diego, we use flat coordinates all the time, latitude and longitude. We use, go forward a couple hundred meters, go back. So it certainly looks flat. And actually, I'm not going to do this now, but if I ask somebody to prove to me that the Earth is round or spherical, they typically can't do it, even some of my PhD students. And if they get that right, I say, prove to me that the sun doesn't orbit around the Earth. And I would say the ratio is about 99.9, to 1 or so that cannot do it. Even professionals, and they don't know their own history. And it saddens me sometimes. But
there was a guy in the desert who figured out that the sun was, or that the Earth orbited the sun based on where the shadow of the sun was, right?
So that's that the Earth was spherical. That's right.
Okay,
so that was Aristophanes and people going back 2,000 years ago. So it's a myth that Columbus proved that the Earth is right. No, he knew the Earth was right. So what are these different shapes? Well, one is, here's a crystal ball. So I'm looking into my crystal ball. So this is a sphere. But if I zoom in really close, it's like being on the Earth. It looks like it's locally flat. And there's another type of shape that there's only 3 classes of shapes in 3 dimensions of space, which we inhabit. There are only 3 dimensions of space that 3 different curvatures that you can have. You can have a positively curved spherical surface. You can have a flat surface. So here's my crystal cube. In other words, where you could draw a triangle on any one of these 6 surfaces, and the angles inside the triangle will always add up to 180 degrees. So that's a principle of Euclid that goes back over 2,000 years, that on a planar surface, on a 2-dimensional surface, parallel lines never intersect, and you can make triangles whose interior angles, 60, 60, 60, or 90, 45, 45, they always add up to 180 degrees. But once you go to a sphere, you can draw 2 lines. You can go to Austin and San Diego and draw 2 parallel lines from our locations, send them both north. They'll converge at the North Pole. So parallel lines meet in a curved geometry.
Right.
When we say, cosmologists say the universe is flat, it means any triangle we make, no matter if it's 3 planets in our solar system, no matter if it's 3 stars in our galaxy, no matter if it's 3 galaxies in the universe, and we connect them as a triangle, the angle inside will always add up to 180 degrees.
So what does that tell us then about the structure of the universe?
It tells us that space-time is flat, at least on the scales, the biggest scales that we can possibly measure, which go out to what I study called the cosmic microwave background, which go back to 13.8 billion years ago, or just 300,000 years after the Big Bang. Now, those are just words, right? I'm just saying space is flat. You can make these triangles, and the biggest triangles we possibly make, they always have this feature that their angles add up to 180 degrees. But you asked a more perspicacious question, which is why? And that's the mystery that we're trying to solve with these cosmic experiments. So if I ask you, Dan, how many different radii of curvature can there be for a sphere? How many different possible spheres are there?
And there's I would assume an infinite amount.
Yeah. And how many different, the other shape is called negative curvature. It's like a Pringle chip,
right,
or a saddle shape. How many different negative curvature, radii of curvature are there?
Infinite as well, right? I mean, it's
infinite.
It's the same, right?
Yeah. Yeah. But zero curvature objects, how many different zero curvature objects are there?
Zero curvature, 3, right? I mean, it's like a triangle, right?
Well, there's just one. In other words, all
I
flat.
See what you're saying,
yeah. So 0 of anything is the same. Like if I say you have 0 bananas, that's the same as if you have 0 apples, right?
Yeah.
But that's a unique property of the number 0, that you don't need units to describe it. So that means you have to explain, why did our universe, out of all these by infinite, in other words, 2 times possibilities of infinite, it could be infinite negative, it could be infinite positive curvature like a sphere, of infinite radii, or anything below. Why did it pick the only value for its spatial curvature that is zero. That has a probability, Dan, of zero, right? It's 0 out of 2 times infinity, that probability, or 1 out of 2 times infinity. So it's mind-blowing. And that's what we're trying to discover. There's a theory that we talked about the first time I think I came on what was your old one called? American Party, American Party, yeah, and the Drinkin Bros. I was on that, and we talked about inflation, not the Bidenomics, and we're not going to get into politics, right? But there's something called inflation, which purports to expand the observation that Hubble made 100 years ago, which is that the universe is expanding. Well, again, what we want to answer is the question why. Not just what is the value? The value is it's expanding 70 kilometers per second on a megaparsec scale. Who cares? Why did it start expanding? The theory of inflation seems to explain that via what's called a quantum field. And I talk about that in greater length in my book. But the point being, when we look back to the early universe, we have to explain a whole host of features. And it's the theorist's job, the Brian Cox, the Brian Greene, the Neil deGrasse Tyson. It's their job to come up with the crazy kind of ideas. But if they're wrong, they can only need to be right once. It's like the enemy, right? The enemy only needs to get you once. You have to be right every freaking day. And in this case, the theorist can be wrong all day long. And then one day she comes up with a theory and it's right. Okay, fine. I have to, kind of be constantly on guard for this corruption of the information. And to do that, we have to build really sophisticated instruments. And that's what we're doing in Chile right now.
Yeah, it's great. So about inflation, didn't we used to think it was the Big Bang, then a period of inflation, and now we've reversed that? To me, it sounds like, I don't know what you know about explosions generally, or explosions inside of an atmosphere, I guess.
I've changed a lot of diapers, Dan.
Well, no. So I'm talking about an overpressure wave where the energy from the explosion literally pushes the atmosphere out, right? It's a concussive wave. It sounds a lot like the early universe before it was filled with matter was almost like an atmosphere, right? If that is indeed the case, if there was a point of explosion and then before we see all the debris come out, there's a wave that comes out, that to me says atmosphere.
There's a lot to what you're saying that we should unpack. But let me just say this. You already mentioned that there is no center of the universe. There is no ordinary matter in the universe. So what you're describing, we would, if I can translate that into modern, physics language, what you're describing is a fluid, which an atmosphere is a fluid, right? But this fluid is what's called in quantum physics called a quantum scalar field. Now, we only know of one example of a quantum scalar field, and that's called the Higgs boson that we discussed briefly earlier. So these things do exist. They pervade all of space and time like a fluid. And then when we see a particle, it's a particular vibration or resonance of that shaking up of that jello-like atmosphere, if you like.
Right.
These are very hand-waving arguments, but for our purposes, it's fine. Now, quantum fields have this peculiar property that they do two things. If they have just the right qualitative properties, they will undoubtedly, their pressure will be negative. They kind of act like anti-gravity. So whereas gravity, you think there's tons of literally billions, trillions of tons of matter in the universe and the Earth alone, right? So matter always attracts gravitationally. Gravitation doesn't have an anti-force the way that electricity has and magnetism have repulsive charges or repulsive poles. Well, there is no repulsive gravity, or so we used to think. But if something called the inflaton quantum scalar field existed, back in the first moments of after the universe came into existence. So after the Big Bang, when space-time of our universe is coming into existence, we don't understand that. That requires what's called quantum gravity. That's another podcast. But that, assuming that it did exist, the universe was filled everywhere with an atmosphere. We'll call it the Hollaway field. That field was expanding by virtue of the fact that it is a quantum scalar field. So you're absolutely right. And that would provide anti-gravity. What's the other thing that quantum mechanics that you may have heard about? Uncertainty, fluctuations, perturbations. So it's not a pressure wave in that, which is an instantiation of a single perturbation. It's perturbations on all scales. So imagine a wave at every single spatial frequency. Not just like the size of the grenade. Like
matter and light, everything is all at the same time. That's fucked up.
Infinite grenades. Imagine these concussive grenades. But there's infinite sizes, so they're creating explosions and pressure waves on all scales. Some of them will have just the right scale. This is mind-blowing. That when the universe became filled with matter, it had some size. It had expanded from an infinitesimal point to a couple 100,000 light years in diameter. There was one wave that will have exactly that wavelength, and that will imprint a pattern that we're looking for in this cosmic signal. So, and then there'll be other waves. There'll be overtones of that wave, right? You've heard overtones like octaves. There'll be another wave that had half that period. And that will imprint another pattern, which we can use to confirm the pattern, and a quarter and an eighth, and et cetera, et cetera. That's exactly what we're looking for with our cosmic telescopes. And I would love to talk more about that, but Dan, I got to go get drilled. Not the fun way of getting drilled, but I got to go get drilled. But I do want to make that offer again to your beloved listener. I really do appreciate every time you host me on here. We got to do another question and answer period on the Nerds or wherever. And that is for these meteorites that I have been misplaced. But yeah, if you guys join, please join the mailing list. I have interviews with Ben Shapiro coming out, Dennis Prager. I know big fans of the stuff that you do, and I also Neil deGrasse Tyson and other things. So yeah, tune into my YouTube channel, Dr. Brian Keating, Twitter, where I follow Dan's every tweet, Dr. Brian Keating, and join the list, briankeating.com/list.
There you go, folks. We'll see you next time.
Thanks, brother.